Hello students, good evening. My name is Shashank Shekhar and we are doing a crash course on chemistry for the upcoming JEE exam. And today is our 14th day. Yesterday we started the chapter that is chemical equilibrium and today we will be completing this chapter. So in the previous class we studied about the equilibrium constant and what is equilibrium and the characteristics of that equilibrium. Today we will be mainly focusing on how the chemical this equilibrium constant can be altered. So we'll see the dependence of this K on different parameters like temperature, pressure, concentration, and various other things. Now we have seen in the earlier class that we have this equilibrium constant has three main characteristics. Yes, so it has three main characteristics, which were that it help in predicting the direction of reaction. The first one was that, and the second one was that it can less this was well, let me write it for you. Okay, the first one was that it help in predicting the direction of reaction, the direction of reaction, and the second one was that it helps in determining the extent of reaction, that how much product or how much reactant will be formed at equilibrium when the reaction is completed. The third thing we have seen that characteristic was dependence on temperature. So we have only seen that yes, this K depends upon temperature, but we have not seen any qualitative analysis upon temperature. So it is true that upon increasing the temperature, we get, you can say, we will rate of forward and backward reaction both increases. But what is the net effect on the equilibrium constant? We do not know. So we will study that today. So we will have a qualitative analysis of temperature effect on the equilibrium constant. So this is the equation that is defined in accordance with temperature, which says that equilibrium constant K is equals to the AI, which is the pre-exponential factor for the forward reaction. This is pre-exponential factor for the uh, this is for the backward reaction. Now, those of you who are not aware about this, so you must have studied this thing in the chemical kinetics. If you have completed a chapter, so that is a term there that is called A or called as pre-exponential factor. Now, it is into multiple into EAR minus EAF, that is activation energy for forward backward reaction minus forward reaction by RT. So this is the formula for K. So you do not need to remember this formula. It is in the middle of the derivation. So next, let us take log on both sides. So we have taken log on both sides. After taking log, this will be log AF by AR, of course. Now this AF and AR are equal, so they will get cancelled because this is for the same reaction. So for the forward and backward, this pre-exponential factor is same. Okay, so we will take log, or you can say net L and ln more precisely. We will take ln here. Then this thing will go off. Ln E is equals to 1 and it will come in this position. So it is written for two different conditions. So if you write it for two different conditions, like if you write that, okay, we have ln k1 is equals to a forward by a backward, or you can say r here. In this case, it is EAR minus EAF by RT. So it is T1, so we will denote it as T1. Similarly, for T2 temperature, it will be this. Okay, so it will be EA minus EAF. So all these values will remain constant because this EA is activation energy, will be same. This will be only T2. So if you divide both of this whole will get cancelled. Okay, so we have taken ln here. Sorry, so we have taken ln here. So it will be something like this. Okay, so this will get cancelled and we will get this equation. Okay, we'll get this equation here, e to the power something, e to the power something, that will be k1 upon k2 is equals to this whole thing and this whole thing whole. Now EA R minus EAF. So I'm not writing this whole derivation right now. So upon when you will put this, you will take ln on both sides, you will get finally this equation. Now this equation is important here. So I have not put a picture of your plot, so let me draw it for you. Sorry for that. So here it is. So it is a energy profile. For those who don't know, it is in the mainly given in this chemical kinetics. So this is reaction progress. So how the reaction is progressing, and is the energy axis. So if you have a if you have a reaction that goes from A to B, and this is the amount of del H we have here. Del H we have here. So this is the enthalpy change during the reaction. You can see that the product is at higher energy. That means it is a endothermic reaction. That is delta H is positive for it. Now suppose this will be called as EAR for the EAF for the forward reaction, and for the backward reaction we will take it from this product thing, so it will be E backward. And if you subtract both of this, you can clearly see that you will get this delta H, that is enthalpy change of reaction. So you can also replace this thing and you will get this equation finally, which is delta H by 2.303 R 1 by T1 minus 1 by T2. So if you are aware about this chemical kinetics chapter and you have studied those formulas, which is A K is equals to A e to the power minus EA by RT, that is of rate constant. This formula is similar to that, but the only difference is here that we are using delta H rather than EA. So if you want to remember it, so this is the formula. Okay. Now let us move to another thing. Now let us see the thermodynamic aspect of this K, that is equilibrium constant. And what is the relation of equilibrium constant with thermodynamics? So let us start. So we know that, so this is the formula that is important one, which says that Gibbs free energy change for any reaction is equals to the Gibbs free energy change at standard condition, that is delta G naught. Here naught represent the standard condition, plus RT, ln Q, where Q you know very well that we have studied in the earlier class also. It is the reaction quotient. So this is the formula that will be used. So it is used multiple times in thermodynamics also, as well as in the you can say in the electrochemistry also, as well as in this chapter, that is equilibrium constant. So you can say overall this formula is very important. Yes. So we have three aspects of this formula. The first aspect is that delta G is negative. So we have seen in the earlier class that if delta G is negative, that the Gibbs free energy is negative, then the reaction is spontaneous. So we know it very well that for a reaction to be spontaneous, the delta G should be negative. And since the delta G is negative, it will proceed in forward direction. But if the delta G is positive, then the reaction is non-spontaneous and will be spontaneous for backward reaction. So if it is a reversible reaction, so suppose we go from A to B and we find that the delta G is -1 and something kilojoule per mole. Now if it is a reversible reaction, then from B to A it will be +1 kilojoule per mole. Okay, so this is the thing that is written here. So if delta G is positive, then in forward direction, of course, it will be non-spontaneous. But if it is a reversible reaction, then in the backward direction, it will be spontaneous. And the third and the last foremost case is that if delta G is 0, that means that the reaction is in equilibrium. So what are the ways? So we will see what happens if the reaction is in equilibrium. So it says that the rate of forward and backward will be the same. Now we'll see the derivation further. What happens to this equation, that is delta G is equals to delta G naught plus RT ln Q. So for at equilibrium, we know that Q is equals to K. also we have seen that delta G is 0. So that equation we have seen earlier, which is delta G is equals to delta G naught plus RT ln Q. Now at equilibrium this equation will transform. So delta G will be 0. So it will be 0. Let delta G naught, and it will be RT ln K. So Q will be equals to K at equilibrium. We know that very well. So final equation will be delta G naught is equals to minus RT ln K. So the same thing is written here also, that is this thing. Now further, if you want, you can take anti-log on both sides. So if we move this here, it will be delta G naught by minus RT is equals to ln K. So if we take anti-log on both sides, anti-natural log, then it will be K is equals to e to the power minus delta G naught by RT. So this is an important equation right now. So we will see the various aspect right now of this delta G naught. So delta G naught can be positive, negative, or equals to 0 also. So we will see how this thing will change. Now the first case is that we are taking the delta G naught is less than 0. Yeah, so that is negative. Now so if this is negative, this whole thing will be positive. Why it will be positive? Because temperature, absolute temperature will be always positive. R has a fixed value, that is 8.314. Now the remaining thing delta G, which is negative, and outside we have a sign of negative, you can see in the formula also. So thus minus minus will become positive, and this whole thing will be greater than 0. So if it is greater than 0, then this whole equation will be also greater than 1. It is clear? So suppose we have E. So e to the power any positive value, that is 1, 2, 3, or any positive value, will always give this whole value as greater than 1. So, and this whole term is equals to K. So it will be K greater than 1. So what does it say? It says that if delta G naught is, you can say negative, then product will be formed in greater amount, because K is greater than 1, and we already know that from law of mass action that K is equals to multiple of this reactant to raised to the power of coefficient. So suppose it is a reactant, it is raised to the power coefficient divided by product, and we can easily see here that it is proportional to this reactant thing. Sorry, this one will be product. Okay, sorry, my mistake. Yeah, so it will be product and it will be reactant. Okay, so it is directly proportional to the product concentration. So if K is greater than 1, so for this value to be greater than 1, this R should be greater than 1, this whole value should be greater than 1. That means it should be, implies that the concentration of P is greater than the concentration of R. Okay, so we will get a greater amount of product. So this is clear for this case. Now the next case we have here is that if delta J naught is greater than 0, that is delta G naught is positive, which means this whole term will be negative from the same in the same way. Now since it is negative, we will get a less than 1 value for this whole thing. So this will have a value that is less than 1. Okay, now since this is equals to K, that means K is also less than 1, which means it is reactant dominant reaction. Reactant dominant. That means reactant will be formed in greater amount. So these are the two cases of this delta G naught. Now next, let us move to this Lee-Chatellier principle. So we have seen the effect of temperature. Now we will see a quantitative analysis, you can say, of all these factors, whether it is this pressure, temperature, and all that, on equilibrium. So we will see their effect on equilibrium and not on equilibrium constant. So make this thing clear in your mind. So that the thing we were studying earlier, we were seeing the effect of temperature on equilibrium constant and not on equilibrium. So equilibrium is a condition, you can say, and equilibrium constant is a value, and it is only and only abrupted when it is when there is a change in temperature. So but equilibrium is a condition, and it may be changed in changing the various parameters. So let us see those parameters one by one. The first one is that effect of concentration. So we will see the effect of concentration. So what happens when we increase or decrease the concentration. The second one is the effect of pressure. The third one is the effect of inert gas addition, and the fourth and the last one is the effect of temperature change. Okay, so we will study one more here. So we will see at the last, that is effect of catalyst. It is not mentioned here. Sorry for that. Okay. Now first we will see the change in concentration. Okay, before that, yes, before that let us state this equilibrium, this Lee-Chatterjee principle. So it is a very important principle throughout the equilibrium chapter. So sorry for missing it. So what does it says? It says that suppose a system is in equilibrium and we disturb it. Okay, now the reaction will proceed in such a direction, means whether backward or forward, so that the change that I have made or someone has made is minimized, or you can say it is countered. So what do you stand by that? So suppose you have a bucket of water. Okay, now if you put your hand in it and splash those water, for a moment this water will, you can say, it can look in a different pattern. You can see patterns of wrinkles there, but at last it will flow in such a way that we will see the initial phase that we have disturbed at the last. So in same way, or you can consider the case of a spring also. So if you push a spring, it will apply force in the opposite direction such that it will regain its size, or you can say regain its shape and size both. Similarly, if you disturb a equilibrium, then the reaction will proceed in the forward or backward direction depending how it can minimize that effect that you have made. Okay, so this is the Lee-Chatterjee principle. Now we'll see the different effects. The first one is the concentration change. So the concentration change is quite simple. It says that if you increase the concentration of reactant, then of course the reaction will proceed to the product side. How is it so? Because initially, suppose the ratio is upon 2x to 1x. Suppose this is the ratio of equilibrium of product to reactant, and if you add this thing something here, this ratio overall will be disturbed. Now to attain this equilibrium again, equilibrium constant again, or you can say equilibrium again, more and more product will be formed, that is reactant will cut into product, so that this equilibrium is attained again. So this is the thing for the reactant. If we add reactant, then the reaction will proceed in forward direction. So if you think it, it is quite simple, that if you add reactant you will get more and more product. Now if it's similarly vice versa, if you add product, the reaction will proceed in backward direction. Okay, so you will get a backward reaction if you add a product, because according to Lee-Chatterjee principle, you have added that extra amount of product. Now to counter that, it will return to its reactant side so that the equilibrium is again maintained. So this is an example from NCERT that I have taken, that is H2I2. So let us see this graph. So this graph looks quite complicated, but is not so. So suppose this reaction is here, it is happening, that is H2 plus I2 and getting at 2HI, and this is the axis of time, and this is the axis of concentration, suppose. Now suppose HI has a concentration like this, I2 has a concentration, this one and this one. Now let us suppose we go from time T equilibrium, suppose we go from T1 to T2 in the first case. Suppose this is T1, which is equal to 0, and this is T2. So in this phase, we do not disturb the equilibrium at all, and we see a quite stable line, that is constant line. The concentration is changing not at all of all these three species. But suppose we disturb the reaction as T is equals to T1. So let us take this T1 here. So we are going from initially from T0 to T1. Okay. Now take it as this T1. So suppose at T1 point we disturb the reaction somewhat. So what we have done here is that we have added this thing called product here. Okay, so this is adding up reactant. So reactant is added in this. Okay, so reactant is added in this, and we have disturbed this equilibrium, right? and we have disturbed this equilibrium in some way. Now it will re-establish this reaction. So between T1 to T2, this time is taken by the reaction to re-establish this equilibrium. Okay. Now since we have added reactant, that is this, and now reactant has to get reduced so that the ratio is maintained and the product has to increase. So this is the added reactant here. Let us denote with a different pen here. So this is the added reactant. Now due to this, if to maintain equilibrium, both of the reactant, that is H2 and I2, get reduced. You can see clearly here that if even though we have not added I2, the I2 concentration is decreased in some amount, and similar goes for the H2. They happen in such a way that the equilibrium is maintained more, and you can see clearly that HI concentration is increasing, and after some time all of this concentration becomes equal. All of this concentration becomes equal, not constant. So do not get confused with my words. So it is constant. So all of this three concentration become constant after some time, and it is the time taken to establish the equilibrium. Then after T2, we have back our, so at time T, which is greater than T2, we have our equilibrium back. Equilibrium back. Yes. So this is the pictorial representation of what happens to concentration when we add a amount of product reactant to a already established equilibrium. Okay. Now next, let us see the effect of pressure on it. So what happens if we increase or decrease pressure? So suppose we are increasing the pressure. Now what will happen is that the equilibrium will shift where, to the side which has the fewer number of moles of gas. Why is it so? So if you look directly into this equation that is called the ideal gas equation, which says that PV is equals to nRT, you can see clearly that pressure is directly proportional to N. Now if you have increased the pressure, so now according to Le-Chatelier principle, the reaction will proceed in such a way that the pressure should decrease. So how it can do so? What it does is that it significantly reduces number of moles so that pressure also get reduced. Now it will depend on the reaction whether which ones has more number of moles. So if we have increased the pressure and the number of moles on reactant is more, so now the reactant will go to the product side and vice versa. So these are the two cases. Let us take an example to explain it. Suppose this we have a reaction here. Now let us see which has the more number of moles. So we can see clearly that the reactant side has mole number of moles. It has 3 moles of gas, 3 moles, and it has 2 moles. Now if we increase the pressure here, the reaction will proceed in which direction? Which has a lesser number of moles, because P is directly proportional to number of moles. So we can see here that the product side has fewer number of moles. So to counteract this increase in pressure, the reaction will shift in forward direction. That is in the forward direction. So I'm not writing it here. So for forward direction, that is equilibrium will shift to right. The right means forward direction. Okay. Now more and more sulfur dioxide will be formed. Similarly, if we would have decreased this pressure, then the reaction would have been proceed to the left side, that is the backward direction, such that it has greater number of moles, that is 3 moles. So this is the direct application of this Le-Chatelier principle. Now next we will see the effect of temperature. So what happens when we change the temperature? So it depends upon what type of reaction we are considering. Means the effect of temperature and the effect of pressure both is dependent upon the criteria of this reaction that we are taking, the specificity of the reaction. So it depends on the number of moles and the thermodynamic aspects. So for the reaction of change of pressure, we see the thermodynamic. So we see the equation, simply the chemical equation. But in case of temperature, we have to be aware about this thermodynamic aspect of this reaction. So suppose it is an exothermic reaction. That means the energy is released, or you can say the temperature is increased as we move toward the product. So it is simple. So for exothermic reaction, we get some amount of heat, and if we increase the heat, we will increase the temperature. Now what happens if we increase the temperature for an exothermic reaction? So if we increase the temperature manually, or you can say by applying some heat or what, then the reaction will proceed in the backward direction or in the reactant side. Why? Because suppose it is exothermic in the front side, that in the forward direction, then it will be endothermic in the backward direction. What is endothermic? Endothermic means energy is absorbed, and the extra amount of temperature, the heat we have given to increase the temperature, will be absorbed in the backward direction reaction, so that the effect of the Le Chatelier principle is maintained. Similarly, for the endothermic reaction, if the temperature is increased, the reaction will proceed in the forward direction. It is clear and very clear. So as we increase the temperature, the reaction is endothermic, that is, it releases heat on the forward direction reaction. So it will absorb that heat and reaction will proceed more forward on the product side. Okay. So this is the effect of temperature. So let us take an example here. So this is the bond cycle. This is the say we have the processing of ammonia. This reaction is exothermic. Okay. So according to Le Chatelier principle, if we increase the temperature, so some amount of heat is produced during this reaction. So if we increase this temperature, this reaction will proceed in this backward form. Backward, according to Le Chatelier principle of increasing temperature. Temperature increase, and it will go in the backward direction, forward direction if we decrease the temperature. Why? If we decrease the temperature, reaction will go forward. Okay. So this both are the consequences of this Le Chatelier principle. Now let us move to our next effect, that is effect of inert gas addition. So what do we do is that we add an inert gas at constant volume. The condition is quite specified here, and you will see specified condition like this in the coming questions also. So we are adding an inert gas at constant pressure. Now addition of inert gas at constant volume do not have any effect in the reactant or product side. So keep it in your mind and always. So if we add something like this, you can say noble gas to this reaction at constant volume, you will not see an effect of this addition. Okay. So this is the thing here. Now, how do we explain this? So first explanation is that why inert gas do not have any effect is that because it is not participating in the reaction at all. Since it is inert, it will not participate in this reaction. The first thing is that, and the second thing is that the partial pressure remains same upon addition of inert gas because the volume is kept constant. Okay. Next, you will see the effect of catalyst. So it was not mentioned here, there. So I will see this thing here. Now, what does this effect catalyst does? So if you look at the reaction profile, this thing. So suppose this is the reaction profile without the catalyst. So I'm not given these pictures here because you will study this thing more briefly in this chemical kinetics, but I'm just giving a overview so you can understand the effect of catalyst on equilibrium. So what does equilibrium does? So this is the activation energy that is required to do the reaction. So activation energy is reduced in case of addition of catalyst. So you can clearly see that this is the energy gap that can be seen. Now due to this, the you can say the rate of forward and backward reaction both increases at the same amount, and so it has no effect on the equilibrium. So equilibrium is not changed in any effect because it increases the rate of forward and backward reaction in the same amount. Of course we get more product, but the equilibrium is not changed. So the equilibrium is not disturbed, it sees the same concentration. So two things that do not have any effect on this equilibrium is that the first one is the addition of catalyst, and the second one is the addition of inert gas at constant volume. Okay. So this was the Le-Chatelier principle. Okay. Now let us see some questions. So these questions are from yesterday, so I'm just giving it a quick overview again because some were done wrongly. Now it says that a vessel is kept at 1000 Kelvin. So this is Kelvin, sorry. Contains CO2 with a pressure of 0.5 atm. So what is given? First of all, Kp contains CO2. Also, so the initial pressure of CO2 is 0.5 atm. Now some of the CO2 is converted into CO on the addition of graphite. So what is the equation that we can find? That CO2 on addition of graphite gets converted into CO. 2 CO for balanced equation. It will be gaseous. Okay. Now what happens? The total pressure is kept at 0.8. So it is the equilibrium pressure. So at equilibrium this pressure is 0.8. Now what happens is that, so initially it is 0.5, this is 0, this is 0. Now upon addition of this, some of this will get, you can say, consumed. It will have X amount of this. Now since it is pressure, so it will not apply pressure, it will be 0 because it's solid. Okay, so this is, I have taught in the earlier class also. And we will get of 2x because 1 mole will react and 2 mole will get, so it will be 2x. And it is said that the addition of all this pressure term is equals to 0.8. So if you find it, so it will be x is equals to 0.8 minus 0.5, it is 0.3. So this is the value of x here. And what you have to find finally, we have to find Kp. So Kp is equals to, we know that the pressure of this thing, that is product. So 2 into x, that is 0.6. Since it is having coefficient 2, so it will be squared. Similarly, 0.5 minus 0.3, that is 0.2. So this is the final Kp do we have here. So if you calculate it, you will get it as 0.1 atm. So the solution is given here also. You can see it. Okay, so it is initially 0.5, then some amount is get reduced. Then at equilibrium it is said that is equals to 0.8. Sorry. So we get it 0.3. Then Kp, we know the formula. If we calculated it, we got it 1.8 atm. That is the final answer. Okay. So let us move to next question. So it is given that for a reaction, we do have this 3-liter vessel and we have this 1, 2 and 4 moles of A, B and C respectively. If Kc for the reaction is 10, so it is given the Kc for the reaction. You have to find which direction the reaction will proceed. So for the prediction of the direction of reaction, we have to find the Q, and if we find out that Q is less than K, then reaction will proceed in forward direction, and if Q is greater than K, the reaction will proceed in backward direction. So if Q is less than K, then forward. Q is greater than K, then backward. So let us find Q. So what is Q? So we will find, we have to have the QC. So we are finding a QC here. So it will be number of moles per unit volume. Why? Because we need the concentration, we know the volume. So it will be, so let us see for A and B. So A and B are 1 and 2. 1 by 3 of Q, 2 by 3 of Q, 1 by 3 and 2 by 3. And what is the product? It is 4 by 3. And since coefficient is 3, we have to cube it. So if you calculate it, you will get it as 10.66, which is greater than this 10. Therefore, Q is greater than K and the reaction will proceed in backward direction. So this is the correct answer. So we can calculate it like this. So we'll get 10.66. So it is almost the value maybe in backward direction. Okay. Now let us move to next question. So it is given that we have a reaction here, that is 2NoCl goes to 2NO plus Cl2. We have to calculate the standard equilibrium constant, that is K, and give the value of delta H naught and delta S naught are given. Okay, and the temperature is also mentioned here. So for this, you have to be aware about this thermodynamic formula which says that delta G is equals to delta H minus T delta S. So this equation you should be aware about it. So it is given, we have to find the delta, so we have to find the k. So we know the relation between delta G naught, so at equilibrium it is given, so it is minus RT ln k. This is the formula. So we first need this delta G naught. We have this delta H naught and S naught. So what are the values? 77.2, 77.2 and 122. 77.2 minus 122. Also the value of temperature is given in Kelvin only, so we do not need to change it. So if you find out this, we'll get a value. So I am not doing this calculation here. So we'll get a value of 40488. So it will be delta G naught, sorry. Yes. Now we know the formula here, that is delta G naught is equal to minus RT ln k. So if we take the log on both sides, that is log, so NT log we will take, that is 10 to the power something. So if you put this values here, you will get a final answer. Okay. Now next, let us move to another question here. So it says that the equilibrium constant at 298 Kelvin for a given reaction is 100. And if the initial concentration of all the species are 1m, then equilibrium constant will be, equilibrium concentration of D will be. So we have to find the equilibrium concentration of D. The value of equilibrium constant is given 100 and initially they have 1 mole. So the reaction is such that AB gives CD. So initially they have 1 mole, 1 mole, 1 mole, 1 mole. So if you find out Q here, so it will be of course 1. And we know that K is given 100. So since Q is less than K, the reaction will move in forward direction. So these are the things we will do first. Now it will move in forward direction, that is A will be consumed and C and A will be formed. Now 1 mole is reacting with 1 mole, so simply it will be 1 minus X, 1 minus X. So 1 mole of each will be reacted, we will get it 1 plus X and 1 plus X. So let us say that it is at equilibrium. We have this condition and it is at t equals to 0. So how we will write this equilibrium constant formula? It will be 1 plus x into 1 plus x, that is reactant product multiple 1 minus x and 1 minus x. And this value is given as 100. Okay. So we will find this using the formula that I have given. So this is the same thing written here initially, and 1 minus x and 1 plus x. So we get this. We put the value and we get it as 9 by 11. Okay. So this is the final answer. So 11 by 9, what does it mean? It is 0 point. It is 0 point. This one. Any of these two. So it was 9 by 11. It will be 90. So 11 8. So this will be the correct answer. Now let us see the next question. So it says that at chemical equilibrium, what is the characteristic? The enthalpy of system is minimum. We do not know about the enthalpy. Enthalpy is almost not dependent on this equilibrium. At equilibrium, the entropy of the system is maximum. Nothing is such said about this. This point is worth noting. So we have already seen that for equilibrium, this delta G becomes 0. So this is the correct answer. Okay. Now let us move to next question. So it says that the equilibrium constant for the reaction H2 to plus S H2S is 18.5 at 920.25. Okay. And 9.25 at 1000. Calculate the enthalpy of the reaction. So it is Kelvin here. Sorry, Kelvin here, not Kp. Okay. Now we know the formula very well, which says that ln k1 by k2 is equals to delta H by 2.303 R is equals to 1 by T1 minus 1 by T2. So we do have this T1, we do have this T2 in the correct unit. We do have this K1, we do have this K2. So we'll put this values here. So using this relation, we know. So we have just simply moved this relation further forward. If you write this, what does it implies? Implies that T2 will multiply it on this side minus T1, which will be T2 T1. So this same thing is written here. Now we'll put this values here. Okay. Now we'll get this. So this is the final answer. Okay. This is clear. Right. Now let us move to another question here, which says that for a given reaction, we have this equilibrium as 100. So N2 plus 2O2 gives 2 and this is the multiple select. So let me make it clear. Earlier time also it is a multiple select type. And what do we have to find? We have to find this equilibrium constant for this two equations. First one is this and second one is this. So we have seen in the earlier class what happens if you reverse the reaction, what happens if you multiply it with a constant. So if you reverse the reaction, we get the reciprocal of the equilibrium constant, and if we multiply it by a factor, then k is raised to that same factor. So these are two things, and if we add two add reactions, then the equilibrium constant get multiplied. So if you compare this and this equation, they are nothing but the reversal of each other. So if we reverse this equation, we'll get this equation. So if we are reversing it, we will get this reciprocal, that is 1 by 100. So for this, it will be 0.01 because 10 to the power minus 2 is equals to 0.01. So this is the first one answer. The second one is, it is multiplied by factor of 1 by 2. So you can see clearly that it's 2 is not here, not here. So if you multiply it by 1 by 2 whole equation, so it is also 1 by 2. So this is left here, sorry. So if you multiply the 1 by 2, then this will be raised to the power 1 by 2. So that will be equals to 0.1. So this is the correct answer. So this is the answer and this is the answer. Just two other answers of this questions. Okay. So same things written here. So we do reverse this reaction. We get this equivalent constant opposite sign. Sorry, reciprocal. Then we have this multiplying by half. So we'll take a raised to the power half, which is 0.1. So it is done in different manner, which is longer. So I have told the shorter one. In which of the reaction following equilibrium Kp and Kc are same? So what is the relation between Kp and Kc? Kp is equals to Kc RT delta Ng. So if delta Ng is equals to 0, this RT to the power 0 is equals to 1, that is Kp is equals to Kc. So it says that which of the following reaction Kp, Kc are not equal. So in that it will be not equal where delta Ng is not equals to 0. So if we compare this to this reaction, it will be 0. Why? Because here 2 moles, 2 minus 2, that is 0. We calculate it for this. 2, 2, 2 on both sides, it is again 0. For delta Ng for this. So 2 minus 1, 1, that is 0. At last we have this, that is delta Ng is equals to 2 minus 1. Oh, so do not include this one, it is solid, so apply no pressure. So 2 minus 1, it will be 1. So we will get some value of RT to the power 1. Therefore, in this case, Kp is not equals to Kc. So the solution is given here. So for this one, we get it as something else, that is Kp is not equals to Kc. Okay. Now let us move to next question. So for the given reaction, it is said that delta H is equals to minus 57.2 and Kc is equals to 1.7 into 10 to the power 16. So which of the following statement is correct? So it is not Kc, it is Kp, sorry. So it is a single answer correct type. So do not include this S, okay. So if we increase the pressure, what will happen? So if we increase the pressure, the reaction will proceed in such a direction that this Kp here. So this statement, okay. So if we increase the pressure here, so we can see that the number of moles is more on the reactant side. So the reaction will move to this product side. So this is correct. The reaction of inert gas at constant volume will have no effect at equilibrium. So it is also correct. We have seen this thing earlier. So this is correct and this one is correct. The equilibrium constant is large, suggestive of the reaction that it will go to completion, so no catalyst is required. So it is also true. We can see that it has a large value, that is 10 to the power 16. So we so it is seen that it helps in predicting the extent of reaction, and we can see the correct application here in this question as well. The equilibrium constant decreases as the temperature is increased. It is not correct. Why? Because equilibrium constant do not have a, okay, so constant decreases as we increase the temperature. So why it is wrong? Because equilibrium constant value does not decrease but it increase if we increase this thing. So it is not that thing, it is we can say that whether it will happen or not, so it is not predictable just by this thing. We need some extra thing like delta H. Okay, so delta H is given here, na? Okay, yeah. So we have this delta H, that is equals to delta H is equals to minus 57.2. Since it is negative, so as we will increase the temperature, so in this case this reaction is exothermic, that is that is we are getting some amount of heat release. So if we increase this temperature, then the reaction will shift in the backward direction. Equilibrium constant decreases. Equilibrium constant decreases as we increase the temperature. So we do know the relation between this equilibrium constant and this. So it says that K is equals to A R by AF into e to the power minus EA by RT. So if we increase this temperature, this whole term will get reduced and this will get increased. So we'll get a greater value of K. So this is wrong. Okay, so A, B, and C are correct. Okay, let us move to another question. So this is the last question I am doing. So after that, these questions I will show you. You have just to attempt this question by yourself. So it says that the correct relationship between free energy change in a reaction and the corresponding is this. So we know it very well. This is the correct equation. We have seen also that delta G is equals to delta G naught plus RT ln Q. So if we are using this pressure, then it will be QP. So at equilibrium, QP is equals to KP, and delta G is equals to 0, which says that delta G naught is equals to minus RT ln KP. So this is the final equation we have. Okay. So this is the correct answer. This one. Yes. Same thing is written here. So these are some questions you have to do it by yourself. So I'm just taking a bit to slide these questions, then you will do it by yourself. Okay, so you have seen this. Then we have, so you can take the screenshots as well. I'm just passing those questions one by one, so you can solve it by yourself. The last question we have, that is 50, that is 20 example. Okay. So thank you for your time. So this was all for about chemical equilibrium. In the next class, we will start this ion equilibrium, which is also a part of this equilibrium chapter. Thank you.